Millions of cars, thousands of kilometers covered every day on the network across an entire country. French motorways count among the most advanced of its kind, and 3 of them are absolute benchmarks, with infrastructures beating all records of civil engineering. There's the A40, a dizzying achievement that holds the record for construction work in extreme conditions.
Its viaducts and tunnels are anything but ordinary.
When planned, the Paris Ring Road seemed a crazy adventure. How did its builders manage to cut a swathe through a densely populated metropolis?
It's the busiest road in Europe.
How did they succeed in building a bridge over a marshalling yard in the middle of Paris?
The main span is 160 meters long, so you don't have a support for 160 meters.
The A10 between Paris and Bordeaux is the longest motorway in all of France. 557 kilometers, more than the length of Ireland. A motorway designed to cope with all weather conditions. The A10, the A40, and the Paris Ring Road each are masterpieces of civil engineering. The history of French highways is fairly recent. The first studies on a new kind of highway, intended to speed up overland traffic, go back to 1927. Yet lack of adequate construction techniques and World War II postponed the project for about 20 years.
The first French highway was opened in 1946 between Saint-Cloud and Orgeval, the autoroute of the West.
However, the use of motorways has yet to be learned.
People did U-turns crossing the median, as there were neither guardrails nor any other separations between the lanes. Some would stop on the hard shoulders, get out the camping table and have a picnic.
Motorways are a novelty. Only with the creation of an entire network do people become accustomed to their use. And from the 1950s onward, it extends ever further. Today, there are 142 motorways across the country, totaling 11,000 kilometers. Due to the toll system, they're the most expensive roads in Europe. Yet, when it comes to the quality of their surfaces, safety, and cleanliness, they set standards unique in the world. One of them is considered one of the most beautiful emblems of civil engineering. The A40 links the city of Mâcon in Burgundy to Switzerland. It's a succession of great feats, holding the record for engineering structures in an extreme environment, the heart of the Alps.
It's an extraordinary achievement. The A40 is really a three-dimensional motorway. It goes up, it goes down, it crosses mountains and spans valleys. For that you need viaducts and tunnels.
Each of these works is a technical feat, given the number of problems involved.
A mountain massif is an immense challenge for infrastructure designers. Building a motorway high up in anything but favorable conditions is also a most intense human adventure. Yet, there is an increasingly urgent need to facilitate trade between France, Switzerland, and Italy. In the early 1950s, the country's economy demands the creation of a new overland route. But the terrain blocks any project for a long time.
The plans have ripened over perhaps 20 years.
Once the project is given the go-ahead, the pace of work is exceptional. However, conditions along the planned route of 208 kilometers are difficult.
My teams had to work even in temperatures of up to minus 20 degrees Celsius, day and night.
The number of works needed to connect France to Switzerland is impressive. No less than 12 viaducts and 4 tunnels. The first of which is a technological feat in itself. The Chamois Tunnel.
It's the longest tunnel on the A40. It runs for 3.3 kilometers under the Chamois Plateau, which rises to about 1,000 meters above sea level.
Yet, before starting work on the tunnel proper, the teams need to know the nature of the rocks they are going to encounter. To that end, they dig an exploratory tunnel 3 meters wide. It will pierce the entire width of the mountain. Once finished, it will be joined on its left by a first tube. Then a second tunnel will be added on its right. The exploratory drills reveal that the plateau consists mostly of limestone, which formed 200 million years ago. It's an advantage, as limestone is extremely stable. Yet it's also particularly dense. How do you pierce it? The solution is provided by an exceptional machine.
It was a real technological revolution at the time. We had RoboFour-type tools that were entirely computerized. They would arrive and take up their positions with their sets of 4 arms, which all drilled at the same time. And progress was then displayed to us on computer screens.
The RoboFour allows 165 holes to be placed with extreme precision, which will then be filled with explosives.
We then inserted detonators with a micro delay. The idea was to cause a sort of chain reaction to blow up a maximum mass of stone.
The 30-millisecond delay between the different explosions causes a much more efficient detachment of the rock than if all fuses had exploded at the same time. Thanks to its onboard computer, the RoboFour digs with great precision down to the last centimeter, resulting in a perfectly regular pattern in the wall.
Then we clear the section of rubble.
Astronomical quantities of rock need to be evacuated. Enter the dumpers, American-built monsters of transport.
They're not like the trucks you see every day. They're really big.
Thanks to the efficient placing of the explosives and speedy recovery of the rocks, the drilling of the tunnels, begun in 1978, is completed 6 years later. Next, it's necessary to provide the tunnel with lungs. 2 ventilation sites are thus built at each end. Giant fans suck out exhaust emissions while permanently injecting clean air.
There are 3 ducts in the tunnel ceiling, a central one for the extraction of smoke and stale air, and 2 ducts on the sides for the supply of fresh air.
In 1986, the Chamois Tunnel consists of only a single tube. The second tunnel, parallel to it, wasn't added until a decade later.
In the first tunnel, both directions of traffic passed through the same tube. Only 10 years later, when they dug the second tunnel, did it become possible to provide one-way traffic in each tube.
That's why today, the speed may surprise drivers in here. 110 kilometers per hour in a tunnel is not common. In the Mont Blanc tunnel, it's limited to 70 kilometers per hour. It's not the only surprise for motorists and truck drivers. At the exit of the tunnel, they are confronted with a disconcerting experience. The motorway seems to be taking off.
You come out at the edge of a cliff.
The tunnel leads directly onto one of the most impressive structures ever built in France, the Nantua Viaduct, 80 meters above ground.
There was a big worry when the tunnel opened. Some truckers coming out of it were overcome with vertigo. No kidding. They abandoned their trucks on the road and left on foot.
The Colossus of concrete extends over 1 kilometre with a deck of 11,000 square metres. 10 piers support it, the highest rising up to 77 metres, the equivalent of a 30-storey building. The piers required the pouring of 5,000 cubic metres of concrete. It was one of the most complicated construction phases, as the environment in the Nantua Valley is infernally complex.
It's a very difficult area from a geological point of view. Everything moves.
This problem is inherent to civil engineering in mountainous areas. To avoid any risk, it's necessary to have piers that can resist the hazards of the environment, and to that end, they must be deeply anchored in the ground. The prerequisite for this is particularly deep foundations.
You need a stable base.
Shafts of 5 meters in diameter are then excavated. They can exceed 20 meters in depth until they come to rest on solid rock formations of foolproof stability. Then they're filled with concrete and covered by a shield. On colossal bases of 250 cubic meters of concrete, the workers can thus raise the actual piers at a rate of 2 sections of 4.5 meters per week. Inside, there is a void to keep the pier from being too rigid. It must be able to absorb the movements of the deck during violent gales and not overstretch its supports. The risk is especially high at the first pier.
The underground at this site consists of extremely unstable scree. It's impossible to use any scaffolding.
A hand-dug exploratory shaft 20 meters deep rules out any conventional solution. The shifting scree is a real problem, whereas the other 9 piers of the 1,000-meter deck are perfect.
You still have one end to do, which is called the abutment. So the question is, how do I build that part?
The answer is a first in France. A counterweight in the tunnel. It's an unprecedented concept to compensate for the absence of the final pier.
We would dig a huge cavern, a real cathedral, something 18 meters high, 10 meters wide, and 30 meters deep, inside the cliff.
Positioned just below the tunnel, the block of concrete will support the weight of the last span of the deck, which is considerably longer than the others, 124 meters, more than a soccer stadium. Once the 9 piers are erected and the counterweight is in position, gigantic cranes, more than 100 meters high, move in the 290 blocks that form the final deck. It's made up of 10,000 tons of concrete. But there are also more than 1,500 tons of steel inside, which poses problems of its own.
Since the viaduct is high above the ground, there is an air current on top and below the lanes. And as they're full of metal structures, the cooling is faster and the risk of icing is greater.
That's why this portion of the motorway requires special attention and constant salting during sub-zero periods. Yet the changing temperatures in the mountains could have caused much bigger problems for the entire viaduct.
One of the great advantages of reinforced concrete is that steel and concrete have the same coefficient of expansion. Not many people know that, but if the two materials had different coefficients, it would have been impossible to use them.
The viaduct shrinks in low temperatures and expands in the summer heat. so its length can vary by dozens of centimeters over the year. In 1986, the viaduct was inaugurated with only one lane. In 1996, when the Chamois Tunnel got its second tube, an additional lane was added. It's an impressive example of how civil engineering can overcome a tricky series of difficulties and achieve a formidable end result.
The Chinese, who back then were far from building anything like it, visited the construction site extensively, as did the whole world.
And the visitors did not stop there, since there are other spectacular sites on the A40, like the viaduct of Ceylon. Less spectacular than its Nantua counterpart, it's nevertheless exceptional. The way it hugs the mountain required all the engineering expertise of its time, since here too, the terrain poses truly mountainous problems.
The whole upper part of the area is gravel scree, which permanently slides down to the lake.
It's extremely dangerous ground when having to move equipment weighing dozens of tons. Erecting cranes where they would be most needed is simply out of the question, as the ground could give way if the loads were too heavy. So, how to implement what seemed impossible to many experts? How to create solid supports for each of the piers along the viaduct?
The foundations were a feat in themselves.
They required exceptional ingenuity and adaptation of the geological features. Placing the supports of the future motorway begins.
Each foundation is a huge well, 4 meters in diameter, until solid rock is reached.
Depending on the terrain, the wells can go down from 6 to 35 meters. Digging in scree calls for exceptional precautions. The engineers create a unique mechanism.
We had machines with cylinders arranged in a star shape that would press against the sides, so that the entire contraption was suspended and could dig below it.
A miniature excavator fills metal buckets that are lifted by a winch attached to the Moroccan well, a process that is effective as it ensures the safety of workers on the ground. The Moroccan well thus covers a layer of scree of several dozen meters. To prevent any sliding of the rocks, a ring of concrete 6 meters in diameter is added. This shell is then attached to the solid rock of the mountain by a kind of metallic braid.
Those steel cables are put under several tons of tension.
By anchoring the head of the well, the impact of any movements of the ground is lessened. Structures that have to resist the pressure of thousands of tons sliding towards them are an exceptional challenge for civil engineering. Yet the groundwork apart, there's another decisive innovation, and it concerns the deck of the viaduct.
The designers opted for a light structure.
Due to a reduction in mass, the piers exert less pressure on their supports and on the foundations.
We're in active scree, so it's all about reducing the effect on the substrata.
Yet which elements can be spared without endangering the structure?
The idea was basically saying, we're going to hollow out the thing along the sides.
Dispensing with tons of concrete by designing a new structure would considerably reduce the overall weight. It's the brainchild of French engineer Pierre Richard. He plans to lighten the parts of the viaduct that have to take the pressure of the deck's weight.
His idea was to say, I'm only going to use concrete at specific points. I'll put diagonals where compression and tractions occur, and everything else is useless, so it can be left void.
The result is a spectacular lace of concrete all along the 1,266 meters of the section along the lake of Ceylon.
That way, we saved 30% of mass, which is enormous, a real technological feat.
It's a world first. In 1989, the Ceylon Viaduct and its lattice work are acclaimed the world over. Yet only one other structure with these specific crosses is ever realized, in Saudi Arabia. The construction technique is simply too complex, as apart from concrete, there are dozens of cables stretched within the viaduct. Since the cables are not protected from rain, frost or wind, corrosion may eat away at the material and weaken the viaduct. Sensors are put in place to detect any brittleness of the cables. The Ceylon Viaduct is regularly checked, inside, but also further up. As the massif above lives, breathes, and at times releases dangerous landslides. So, as early as the construction of the viaduct, cliff motion detectors are implanted.
These sensors continuously record the movements of the mountain and alert us of any potential cracks.
To avoid disaster, additional precautionary measures have been added. It's demanding work, even for experienced mountaineers.
We have to clear the brush at the top of the cliff and then provide secure access to the edge. There are handrails everywhere, yet we have to work hanging on our ropes. It's a tricky job.
Their task is to nail the fragile mass of rocks to the more massive layers several meters inside the mountain. It's done by inserting rods 8 meters long and weighing 80 kilograms each. A machine helps to drill the rock. The compressed air device is moved every 2 meters by helicopter to allow the operators to perfectly square the sensitive surface. The rod is driven into the hard rock. Then cement grout is injected to seal it.
Once the grout overflows, the injection has worked.
All the while, during these operations, the rock is covered by a net, as conditions are delicate.
When faced with nature, you have to remain a bit humble, as we don't really know in what state the overhang is, if it's close to falling, or if it will hold.
A fence at the bottom of the cliffs is intended to retain or slow down any falling rocks. Drilling in a fragile mass compels the installation of yet another sensor. If the cliff shows signs of violent movement, it sends an immediate signal which activates the instant closing of the motorway. When the A40 was inaugurated in 1990, after 17 years of work, not all these safety measures had been implanted yet. Anyway, it had been an outstanding effort. The then President of the Republic, François Mitterrand, called it the Motorway of Titans.
Delegations came from Northern Europe, from Japan, I think even from Australia and the United States. It's proof that people were indeed interested in this site because of the density of works along the route.
The A40 holds the record for exceptional engineering structures along its 208 kilometers. It's a showcase of civil engineering, as is another legendary motorway. The Paris Ring Road, a motorway in the heart of a metropolis. The 35-kilometer ring road is essential to the traffic in the French capital. 500 million vehicles use it every year.
That's more than 1 million cars a day.
It's a record in Europe. It also required a hitherto unseen array of infrastructures, tunnels, bridges, viaducts. There are more than 140 of them. Building a motorway in one of the most densely populated capitals in Europe, that was the challenge the French set themselves in the 1950s, knowing full well that they would have to overcome difficulties never met before, like demolishing the old Parc des Princes stadium and rebuilding it on the walls of the ring road.
The Parc des Princes and the ring road are made as one.
The ring road must also pass over some 50 railroad tracks. The solution, an unprecedented structure, a cable-stayed bridge in the heart of a city. The ring road is one of the great adventures of civil engineering in the 20th century. The ring road follows the lines of the city's fortifications, dating from 1840. A wall that encloses the entire capital to protect it from assailants. A rampart, surrounded by a deserted area on its outside.
The idea was to have a free space which would force attackers into the open for about 300 meters and thus permit a clear field of fire.
The zone, as it's called, is thus an ideal space to build the future ring road. Work on dismantling it starts in 1956 with the southern part. The guiding idea is to avoid declivities of more than 5%. Yet a first obstacle arises in the west of the city. It's the old stadium of the soccer club of Paris. Alas, there's no other way. With tens of thousands of people living nearby, there's no alternative site available. So, if there's going to be a ring road, the stadium has to go. Yet the city wants to keep its popular arena. It's an impasse.
In the end, the planners came up with a radical approach. They would build the ring road and the new stadium as one.
In 1972, it's a revolutionary idea. Proposed by Roger Talibert, an architect specializing in big sports arenas. The twin project is given the go-ahead. Yet first, the old stadium must be dismantled.
You have to shear off the steel reinforcements as well as grind down the concrete.
As soon as the stadium is gone, construction of the new road can start.
It took the form of a huge trench to accommodate 2x4 lanes for the traffic.
The tunnel is 580 meters long, about 30 meters wide, and 6 meters high to let the biggest trucks pass. A wall separates the two tubes. It also hides massive concrete pillars that will support the weight of the stadium. They are essential for the coherence of the structure. They allow the huge arches to be erected that have since become the signature of the stadium. There are 50 of them, each weighing 25 tons. The result is impressive. It takes 4 years to build the stadium and the tunnel of the ring road underneath. From 1968 to 1972, it's a spectacular sight. The engineers and architect Roger Talibert have won their bet, yet another adventure awaits the builders of this unusual road. Further east, the Masséna marshalling yard blocks the route. And unlike the Parc des Princes stadium, it can't be dismantled.
At Masséna, trains are prepared for the Austerlitz station. It's a huge area where sleeper trains are parked, maintained and cleaned.
Building a tunnel here is impossible, as the ground with its 50 railroad tracks above must not be weakened. After 2 years of studies, engineers propose a solution: a bridge of 492 meters, a length that requires at least 8 piers. Seven piers are feasible, but not one more, which implies that one section of the bridge will be extremely long. The challenge is to find a way to span 160 meters without any support. A slab of concrete that long would collapse. The solution is a first in a dense urban environment: a cable-stayed bridge. A technique that allows a span made of steel and concrete to be held by ultra-resistant cables.
Without these cables, the deck would deform. The traction of the cables ensures that it will stay horizontal.
It's a technique that pushes civil engineering to its limits. In the 1960s, there was no cable-stayed bridge of comparable dimensions. It was necessary to top the piers with 2 pylons, 35 meters high, the size of a 13-story building. Then, 4 cable stays had to be connected on each side. Each stay holds 19 strands. They give the tubes exceptional resistance and allow the thrust to be deviated. With the stays in place, it's time for the crucial tests.
You close the bridge and bring up trucks with a known tonnage.
Sensors measure the deformation of the bridge at its highest point. The Masséna Bridge of the Paris Ring Road is perfectly safe. It's now the longest bridge in Paris at 492 meters. The equivalent of 10 Olympic swimming pools put in line. It cost 2 billion francs, 300 million euros in today's money.
The work then continued westwards with the spanning of the Paris Exhibition Centre.
With 21,600 square meters of exhibition space, its 7 halls and more than 7 million visitors per year, the exhibition centre cannot be circumvented. So here too, it will be obligatory to pass above, with a distance never before seen in the capital. It needs a structure of 860 meters before there's suitable space to continue the ring road. Yet how can spans be built that long while limiting the number of piers? There is an answer that allows the usual limitations to be ignored.
It was a French genius who invented pre-stressing. In 1928, Eugène Freycinet revolutionized the world of construction. Until then, it was impossible to build anything of such dimensions.
The principle is based on the insertion of a cable under tension inside the concrete beam. Thus, the concrete is no longer passive, but active due to the internal pressure. Spans can reach 30 meters without any support. And this is how the longest viaduct in Paris passes over the exhibition centre.
Some halls are directly below the ring road, so when you are in the exhibition centre, the ceiling may be the sub-slab of the ring road.
So far, the engineers have found solutions for each obstacle en route. Alas, an altogether new kind of problem is looming to the west of the capital. When it reaches the Bois de Boulogne, the ring road is stuck. The local residents are strongly opposed to it. They consider it an unbearable nuisance.
Some very influential people did not want the windows of their villas overlooking the ring road.
There isn't really an option except to pass under the forest. But there's an obstacle. The lake of the Bois de Boulogne. How to pass underneath with 30 million litres of water above. However, the lake is artificial, and that changes everything.
These lakes were designed to be emptied, so they installed a system of channels to evacuate the water.
Thus, the transformation of the Bois de Boulogne can start by draining the lake. Sluice gates at the bottom are opened. Gravity does the rest. The workers can go about their job several meters deep without fear of flooding. They dig a trench nearly 600 meters long. It's covered by a new structure, 1 meter thick, which will become the bed of the new lake.
It's a huge slab of concrete which will form not only the ceiling of the ring road, but also the floor on which the lake was recreated.
Once these works are finished, it's time to give back to the forest the vista it had a few months ago. The concrete slab is covered by a layer of asphalt, ensuring that everything is waterproof. Then, tons of earth make up the bed of the lake. All that's left to do is open the valves to let the water in. The lake is thus recreated on the surface. Underneath, there's no longer earth, but a motorway. Yet engineers are worried the water may seep into the tunnel. The material used for its walls and the ceiling is not free of defects.
Concrete is a porous material. It doesn't seem obvious, but air and humidity find their way through it.
The tunnel is inspected several times a year, since 1973, when the ring road was inaugurated. It took 15 years before the final constructions saw the light of day.
Which is extremely fast. 150 major constructions spread over 15 years means the realization of 10 bridges or 10 tunnels per year. It's a feat of civil engineering which is probably unachievable today.
Yet work on the ring road, used by more than 1 million vehicles per day, continues. More than 50% of its length has been covered by a new phonic coating. It reduces traffic noise by 3 decibels, thereby doubling the hearing distance from 50 to 100 meters. The Paris ring road is something of a challenge to those not used to driving on it. In contrast to conventional motorways, priority is given to cars that enter via the access ramps. And there's no emergency lane either.
A pedestrian on a usual highway has a life expectancy of about 20 minutes. On the Paris ring road, it's 6 minutes.
The ring road has achieved legendary status. Yet when it comes to problem solving, it's dwarfed by its big sister, the A10. At 557 kilometers, it's the longest motorway in France. When opened in 1972, the Aquitaine, as the French call it, is a luxurious carpet of asphalt, linking the capital to the hub of the southwest, Bordeaux.
The A10 crosses 11 departments and is connected to 9 other motorways.
Yet several decades later, it faces an increase of traffic never before seen in France.
50 years back, people were far from imagining that the motorway would be such a success.
So the A10 is entering a new era that brings about new challenges. Large parts of the infrastructure have to be demolished and replaced in record time. The new A10 is an emblem of civil engineering, just as when it was built. In 1960, it was intended as the main axis of trade between France and Spain. Back then, the powers that be decreed that the A10 would run as straight as possible.
It was part of the overall conception of motorways. At 130 kilometers per hour, the driver should have several seconds to react if there's an object on the road.
But how to keep the route straight when there are hills and valleys?
Heavy trucks tend to slow down uphill, and once downhill, you have to brake or overtake, which creates disturbances. So the more you manage to create a smooth longitudinal profile, the better.
The solution devised by the engineers is based on the principle of communicating vessels.
When you have a hill and a valley, you dig a trench through the hill and fill the valley bottom with the soil from the trench to achieve as flat a profile as possible. You shift material from the hill into the valley ahead and solidify it.
Moving millions of cubic meters of soil is a colossal effort, as is required on another section of the planned motorway. To pass the city of Tours, the A10 must cross the Loire River. In the late 60s, it's quite a problem.
The Loire is the last wild river in France.
It's not contained by any dam, unlike the Seine or the Rhine.
The floods of the Loire are so powerful that there was no way of regulating them.
So how to cross a river that may wash away everything in its path? What technique in the 1970s would allow a bridge to be built strong enough to withstand the Loire's force? It all depends on the piers. In order to install them in the riverbed, a watertight barrier must be built and pumped dry. A platform of concrete will then provide the foundation.
Next, we lift the pier progressively, element by element.
Each pier is about 10 meters high, yet they're endangered by the river. To protect them from onrushing debris or tree trunks carried by the floods, the designers have added bow-like pointed ends to the supports. There are 16 piers in total. They'll carry the decks of 2 parallel bridges with a lane in each direction.
Each deck is the size of about 2 soccer fields, so it's quite a big structure and also quite complex for the time.
Construction is done piece by piece, using prefabricated blocks ready to be put in place.
The deck is a succession of caissons.
The caissons conceal something unusual. They're hollow. Below the motorway, there are 9,000 square meters of empty space. That's half the size of a supercarrier's hangar deck. A design that provides decisive advantages. The void enables building material to be saved. The caissons are thus less heavy on the piers, and their shape makes the structure much more solid.
They're actually more resistant than a slab of concrete.
To add flexibility, there are supports between the piers and the deck.
They're made of rubber materials that are flexible enough to allow the bridge to move.
It takes 4 years to build the bridge. In 1972, the new motorway can finally pass over the Loire. It's an instant success. The A10 becomes unavoidable. The number of users rises exponentially, as does the wear and tear of the motorway. 50 years on, it's necessary to renew it entirely, especially the Loire Bridge.
Moisture and rain spell death for many concretes. Corrosion of the reinforcements inside makes the concrete crack, and if it crumbles, there'll be disaster.
On April 9, 1978, a part of the Wilson Bridge in Tours collapses. It's a miracle that no one is hurt. Work on the twin bridges over the Loire River represents a special challenge, as tens of thousands of motorists use them daily to go to work. The only solution is to block one overpass and to allow two-way passage on the other bridge. So time is of the essence.
It's rarely been done. Actually, never.
Working at a relentless pace, the builders managed to finish their job in 4 weeks, 2 weeks ahead of the planned schedule. It's a record. Yet sometimes repairing is not enough. In some cases, it's necessary to destroy to be able to rebuild. On the A10, operations like this abound. Thousands of tons of material need to be pulverized. Demolishing a bridge requires all the know-how of civil engineering. It means dismantling tons of scrap metal and concrete in record time, while erecting a brand new bridge a few meters away. That's what the engineers are up against, as the bridges built in the 1960s are no longer up to current traffic conditions.
The lanes were designed for light vehicles, cars or small trucks. Yet over the years, trucks became ever heavier.
To improve the flow of traffic, the A10 is getting additional lanes, going from 2x3 lanes to 2x4 in some places. On a motorway of more than 500 kilometers, it means dozens of construction sites.
To add a fourth lane, new bridges had to be built next to the existing ones, as on the old ones there was no space for an additional lane.
To keep traffic going, the new bridges have to be in place before the old ones can be demolished. It takes 6 months to build a new bridge, and about 10 hours to tear down the previous one.
There's just one night to do it, then the traffic starts again.
Before launching the operation, it's paramount to protect the roadway. If a part of the bridge collapses onto the road, the damage couldn't be repaired before the next morning.
So we spread a bed of sand on the road, a little over 1 meter thick. Yet that's 1,800 tons on average for a single bridge.
An essential precaution, given the impressive blocks and tons of rubble that will fall from the bridge.
Then we'll send in the grinders.
Their clamps are subjected to a severe test. With the reopening of the road approaching at sunrise, what the workers dread most is the breakdown of one of their machines.
There was always a spare in readiness in case one machine would become unusable. We couldn't afford to stand aside and just wait and see if we could reopen the road in the morning.
Nothing must be left on the road, so in one night, a bridge built 50 years ago is a mere memory. An exceptional performance.
In a few hours, a structure made of concrete and steel, supposed to last for decades, is down.
The new bridge built beforehand next to the old one is then opened. The changeover is done in a minute. There are now 3 lanes instead of 2 in each direction. Yet work is not limited to enlarging the motorway. Another major operation consists of digging a ditch on both sides of the motorway. It's meant to recover the rainwater polluted by the hydrocarbons released by the vehicles.
We drive a piece of pipe under the road, weld on another one, until we reach the other side of the motorway.
However, these ditches need a gentle slope, which is not the case here. The Courtenay Valley is the most complex section of the A10. To go from 2x2 lanes to 2x3 and increase the width of the road to 16 meters, there's no choice but to build a new bridge across the valley. Yet the gap between the rocky masses requires impressive works. A viaduct 210 meters long and 30 meters high. And the process is anything but usual.
With a standard viaduct, the steel beams and the precast concrete slabs are made in a factory. You just assemble them on the site. This wasn't the case here.
It's out of the question to block thousands of square meters of land next to the construction site. So, how did the engineers manage to build this twin viaduct? An entirely new way of manufacturing the parts must be found for work on most unfavorable terrain.
We did everything on site. Just bringing in all the raw materials was a challenge in itself.
The voussoirs, the concrete blocks that will constitute the deck, are cast on site. As are the metal reinforcements. They're placed in a mold that's filled with tons of still hot and liquid concrete. Once set, the mold of the future voussoirs is moved forward one notch. An operation much more complex than joining voussoirs arriving from a factory and ready to be installed.
If it's too cold, we can't pour concrete. And if it's too hot, the concrete doesn't dry sufficiently and doesn't have the properties we need. So we had to adjust our schedule constantly.
It takes 22 months to complete this unusual construction of a twin viaduct. Dozens of workers and specialists are involved. The modernization of the A10, the longest motorway in France, is a stunning achievement. New bypasses built in record time, adding additional lanes, and exchanging bridges in a race against time. It's civil engineering at its best. A demonstration of expertise and organization never seen before for a traffic axis that sees more than 80,000 vehicles pass on a peak day. Just like on the A10, construction techniques used to build the A40 have become benchmarks. Its mountainside viaducts are still visited by engineers from all over the world.
There's a whole catalogue of patents that the companies were able to offer internationally.
With more than 140 structures on 35 kilometers in one of the densest urban environments of Europe, the Paris Ring Road is the pride of its builders. One of the next big evolutions will be the electric car and the appropriate adaptation of motorways. France, whose road network is one of the best in the world, is determined to become a precursor in this field. Its civil engineers are ready to embark on new adventures.